All right, today we're going to do more frames and machines. Not frames and machines. We're going to do more beams, which might be part of frames and machines. And actually, we will work one machine problem near the end, or set up one. I don't think we'll work all the way through it. But we're going to start with just pure beams, which might be a part of a frame or a machine. So I made a little T-beam here so that we can get an idea of when I'm drawing these pictures, what it is I'm drawing. Let's start with just working an example, kind of like we did last time, but with more forces on it, more different types of loads, and we can kind of see all the different pieces that we might have to deal with later on. So we'll use a T-beam since I have one, and we'll put a T-beam with some loads applied to it. We'll do a pin. Let's put a roller somewhere, maybe not all the way at the end. You know, normally we do the simply supported with the pin and roller all the way at the ends. But let's put it, somewhere in the middle. So let's draw up something like this, put some more loads on it so we don't have just this. Maybe we'll put this point load at the very end, a distributed load between the supports, and then a concentrated moment over here. We haven't put one of those on one of our beams. So let's draw all of that and go from there. So I'm going to draw a T-beam, so something that is going to represent our T-beam. We'll draw a little flange here on the top, and then the stem. Again, I'm drawing the side view of this, so that would be kind of like that. You can kind of see the top of the flange. Over here we'll draw the cross section, which would be looking at it from the end. So I've got a side view that normally shows where all the loads are, and then we've got the end, the cross-section view that's going to show us where, whoops, off the screen, where neutral axis, things like that. Some dimensions will be on this cross-section. So this would be our little beam that we're drawing a picture of here. I said we were going to have a pin and a roller in here. We're not going to have any forces coming in at angles. Just so that we don't have to deal with what's happening in the X direction. All of our forces are going to be perpendicular to the top of this beam. So let's just say that we have over here at the pin, we have a reaction. We'll call that the reaction at A. We don't know what it is yet, but we know there's a reaction there. So that there would also be a reaction in the X direction. But since there are no other forces in the X direction, we're going to say that this is 0. So you could draw it and zero it out. I'm just not going to draw it. Let's put our roller maybe somewhere in here. Normally we put them on the ends, but let's put it somewhere else just to have a different setup. That'll be the reaction at B. I'm just using A and B as two different points on the beam. Let's put our point load at the very end of the beam. And let's make it relatively large, 5 kips. Let's put our distributed load between these two supports. So let's evenly distributed all the way across there. Something like that. And let's give it a value 2 kips per foot. So 2,000 pounds per foot of length. We'll have to put the dimensions in a minute. Let's also put a concentrated moment in here. We haven't put one of those, but it would look something like this. And it'll be 3,000 kip feet. Or, well, 3,000 pounds, 3 kip. So 3,000 foot-pounds here. So it's kind of like there's something applied to the side of this beam that is twisting. It's wanting to twist it and creating that effect there. So there's something bolted here that's wanting to twist to create that effect. Or welded, to be bolted. All right, let's put some dimensions. Let's say 10 feet, 3 feet. Well, did that one different, didn't I? 2 feet. So 15 foot total length for our beam. And I think that's all we need. So this would be what we're given. Well, with a few other things, we'll need to know what kind of beam it is. We know it's a T-beam, you know, got a T cross section, but we don't know what particular T-beam it is. So we'll need to look at that in a minute. Just moved everything out of the way. So let's say what we want to find. All right, so let's say that we want to find the max flexural stress, or the bending stress. Now, for what we know how to do right now, we can't just say the maximum flexural stress in the beam. Tomorrow we'll be able to do that, but today that would be a little difficult. We could work our way through it possibly, but let's specify at a point 6 feet from the left end of the beam. So in other words, if I measure over from the beam, go over 6 feet, and chop it open right there, what's the stress in that particular section of the beam? And I want to know the maximum one. So not just any stress there, the maximum stress. While we're at it, remember inside here there's a shear force and a bending moment. Let's also calculate the let's call it direct, or maybe transverse shear stress at this same section. So there are actually two different types of shear stress here. The one I'm talking about would be like this. So shearing it, directly shearing it. But there is another shear stress, kind of like if you think of the pages in a book and you bend the book, all of the pages want to slide past one another. I don't have a nice thick book handy. Oh, maybe I do. Here's a big book. So we take a section of the pages and imagine these are all little individual layers of a beam, but they're bound together because they're part of a beam. When I bend these, if you notice the end, and I know it's kind of blurry, but I don't want to refocus on this, the end kind of gets this curve because all of these pages are actually sliding past one another. That sliding past one another is a shear stress, and so there is a shear stress between the layers of the beam, if you think of the beam in layers, that we might also want to calculate. We are not going to calculate that today. This one is the shear stress, just you push hard enough in one point and shear it directly, kind of like you're cutting it with shears or scissors. All right, so we want to find those two things. So the thing that's key about here is that I have specified a point or a distance, this 6 foot section. Without that specification, then I have to know something about the entire beam, which I don't know how to do that yet. So tomorrow we'll figure out how to take this and just say, find the maximum flexural stress in the beam and solve for that. But today that would be a little bit difficult. So if I know I'm going to cut this beam apart right here and look at the inside of it, then I have to decide, or it'd be useful to decide, am I going to look at this side or am I going to look at this side when I draw my free body diagram? I'm going to want to look at this side because that picture looks a whole lot simpler to deal with than that picture. And they're both giving me the same internal shear stress and bending moment. So why not look at the simpler one? So here's the simpler one. It does mean that I need to know what RA is. On this one, I need to know what RB is. So either way, I've got to figure out one of these reactions. So I'm going to take this one, and that means I need to solve for the reaction at A. The easiest way to do that is to take this free body and solve for summation of moments about B. There's point B, and that'll give me a value for RA, and then I can work with just the side I'm interested in. So let's start our solution by doing summation of moments about B equals 0. All right. This is for the whole thing, not for just the little section. So I've got the whole beam here. I already see that I've got a distributed load, and when I'm doing moment equations, it's simpler if I go ahead and lump that distributed load into a single point load. It is 2,000 pounds per foot. It spans 10 feet. So that's a total of 20,000 pounds, or 20 kips. And it spans 10 feet. This is evenly distributed, so I place this lumped load right in the center of this, so the centroid, which would be 5 feet. All right. So RA times its moment arm of 10 feet to point B minus, because it's going to create a counterclockwise moment if I think of just the point load, so minus 20 kips. It has a moment arm of, it's not labeled here, but if this is 10, that's 5, then this is also 5 feet. RB does not create a moment about B. It has a line of action that actually goes directly through point B. This concentrated moment is just plus or minus. It is drawn counterclockwise. I said clockwise is positive, so that's minus 3 kip feet. And then this would go clockwise about B, so plus 5 kips times that moment arm is also 5 feet. I used 5 a lot, I guess. So the only unknown in here is RA. So we should be able to solve for that. So I'm going to move RA to the other side. So minus RA equals, and then we're going to do all this. This is not a negative, that's a times. Or no, that is a negative, sorry. That's a times. So negative 20 times 5 is 100 kip feet. Minus 3 kip feet. This one already has pounds and feet built into it, so I don't multiply times any distance. It's just plus or minus, and in this case it's minus. And then plus 5 times 5, 25 kip feet. And this was RA times 10. I didn't put that. All of this gets divided by that 10 feet. So all the feet cancel out, and I solve for RA. So let's see. Negative 100. Oops. Negative 100 minus 3 plus 25. So this whole term divided by 10. Negative 7.8 kips. So the negative there, let's make sure. Oh, well, but it's negative RA. So RA is actually 7.8 kips. So 7,800 pounds. That seems like a reasonable number for this total. So I'm going to go with that. Okay. Now that we have that piece of information, we could go and solve for RB if we wanted to, maybe kind of do some double checking, but it doesn't help us in solving our actual problem, so I'm not going to do it. We're going to draw this free body diagram. We're going to put it on a new sheet of paper though, because we've kind of ran out of page room here without really getting it crowded up. So I guess that's just one sheet. Feels like two. There it is. All right, so let's take just this piece and draw it. Maybe a little bit bigger so that we have room to write everything. There's where we cut it open. We just found a value for RA of 7,800 pounds, or 7.8 kips. We have this evenly distributed load across the top, so we're going to put that across here. We don't have all of it, but we have 6 feet of it. And it's still the same magnitude, 2,000 pounds per foot. And that's it, right? Only other thing are the internal shear force and internal bending moment. We do have to remember which direction to draw these internal forces. So most of the time I tell you just draw them in the positive direction, or draw it in tension, you know, whatever. These we have to be more specific with, so that things later on will work out. So when you draw a beam and you draw a free body diagram where you've cut the right end of that free body diagram, you put the shear force as positive downwards and the internal bending moment as positive counterclockwise. You don't have to write your equations that way. You have to draw the arrows that way. And just so you, for total completeness, if you were to draw the other side, I'm not going to draw the whole thing, but if you were to draw the other side of the thing, on this side, you would put the shear force positive if it goes up, and the bending moment positive if it's clockwise. So these conventions you have to follow for stuff to work out later on. When we're drawing the pictures of the bending moment and the shear force in the beam, we need these conventions in place. So that's kind of one of the few times that I'll specify you must draw the free body diagram with these directions as positive. All right, so we're using this half. We don't really need that half. And, oh, well, we do know that we cut it at 6 feet, because that was our problem statement. Our problem statement said find the maximum flexural stress at a point 6 feet from the left end. So that's why we cut it at 6 feet. Now I can go here and I can write my two equilibrium equations. Let's write our moment equation about this cut here. Summation of moments about the cut surface. We'll do clockwise as positive. This symbol doesn't matter if you do clockwise or counterclockwise positive. It's these that matter. So this one we can write however we want. So I've got 7.8 kips with a 6-foot moment arm from the cut over to where the line of action for that force is, clockwise. This guy is a distributed load still, so I'm going to go in and put a concentrated load, 2 kips per foot, spanning 6 feet. So this is 12 kips. And this distance would be 3 feet. And so would this one. All right, so that 12 is going around counterclockwise, so minus 12 kips times 3 feet. This 3 feet right here from point to that line of action. V does not go into this moment equation. M does, because it is a moment, and it is negative compared to my symbol here, so minus M. So I'm going to move minus M to the other side, so I get M equals, and then we're going to do this math. 7.8 times 6, oops, I didn't get the 7 in there. 7.8 times 6. This term is 46.8 minus 12 times 3 is 36. 10.8. 10.8 kip feet. It came out positive, so that means that these arrows would all be drawn in the correct orientation. All right, let's do our forces in the y direction. We have 7.8 kips minus 12 kips minus V, oops, that's a W, minus V equals 0. I'm going to move the minus V over here to get V equals, and it's going to come out negative. 12 minus 7.8, negative 4.2. So that just means that this shear force and this one are actually backwards from what they should be, but it doesn't normally matter for this direct shear if you shear this way or if you shear that way. It doesn't normally matter. So that negative sign is not as important as a negative on the bending moment would be. The negative on the bending moment controls whether the beam is bending this way or bending this way. So this would be a positive bending moment. This would be a negative bending moment. In fact, it's really easy to remember. As long as you're using this sign convention, then, and this is not why we use the sign convention this way, but it does work out. So positive bending moment is going to bend the beam this way with tension on the bottom, compression on top. And a negative bending moment is going to do the opposite, tensions on the top, compressions on the bottom. So that by itself is not particularly simple to remember, but if you think of it as positive moments equal that, negative moments equal that, now you'll never forget which way, as long as you're following this sign convention, which way that's going to bend the beam. So a positive bending moment is going to make it bend with a smiley face. Negative moment, if we had calculated this and it became a negative 10, then the beam would be bending this way. So positive moments and negative moments, as long as you're following this convention for your internal M and V. All right, so what do we do with these? Let's see what we were trying to do. We wanted to find the maximum flexural stress here. We know the internal bending moment now. And we wanted to find this transverse shear stress, or the direct shear stress, at that same point, which we have the shear force. So these are not stresses, but they will create stresses. Let's do the shear stress first. It's the simpler of the two. So the shear stress is just tau, and it's the same one that we did at the very beginning when we started this course, where we take the shear force, and it doesn't actually matter that it's negative, but we'll keep the negative sign, 4,200 pounds over the area. Now the area is the cross-sectional area of the T. So we don't really know that, so we need to go back a few steps, all the way back to here, and we need to specify what kind of T this is. So let us look at a chart there where we've got a whole bunch of, these are all WT different numbers. So WT is a wide flange T-beam. So that would be like this cross section where the flange is relatively wide compared to the depth of the beam. I don't know the exact ratio, but it's wide compared to the depth. And let's pick one of these. Let's pick one of the smaller ones. WT 4 by 29. So I'm writing it down over here on our page. Now, in this chart, maybe I can make it a little smaller so we can, well, not that small. WT 4 by 29, that first column is cross-sectional area, 8.55 square inches. 8.55 square inches. So now I can take that and plug it in here, and I'll get pounds per square inch, which will be PSI, and I've got 4,200 pounds over 8.55 square inches, 491.2 PSI. Then I have to decide if that's a lot or not. So we need to know the material that our beam is. So let's say that it is a well, let's look at some materials here. Let's say that it is a 0.4% carbon hot rolled steel. So we have to find some information about this, like in the table here. So there's 0.4% carbon hot rolled steel, and we have the elastic strength, which would be the yield strength. So if we exceed this number, then we have permanently deformed, bent the beam. So that number is 53 KSI, so 53,000 PSI for tension. We just calculated a shear stress though, so the shear number is not listed. And there are several different models for what to calculate as the shear strength. We're using the most simple one where you just take half of the tensile strength. So it's also the most conservative version. So the tensile strength, sigma y, for our material is 53 KSI. So 53,000 PSI. So the yield strength and shear would be half of that. So we just take 53 divided by 2, 26,500 PSI. And we are well below that. We're at 500 PSI. So we have a factor of safety against shear. This is the yielding. Yielding. The yield strength is 26,500 PSI. The shear stress, 491.2 PSI. Our factor of safety is 26,500 divided by 491.2. We have a factor of safety of 53.9. So we definitely have plenty of headroom before this thing begins to shear. And that's normally going to be the case for this direct shear. It's pretty tough to put enough force on a cross section to directly shear it. All right. But let's look and see if there is an issue with this bending moment. So it looks like we need a new page. We already know based on this that at this point in the beam, we have tension on the bottom, compression on the top. All right, so let's say that M at 6 feet is 10.8 kip feet. We're trying to solve the flexural stress equation. Sigma equals negative, that's part of the equation, M times Y over I. We have M, but we don't have this Y and I value. So we need to go back to that chart that we looked at a minute ago where we got the area and find these values. So I'm going to draw a little cross section of our T-beam. So that we can label some things. So let's find, oh, what did we use? We used a WT 4x29, so down here. So now I have these other columns. I have depth of T, I need that. So remember, this is nominal depth in the name over here. WT4 means it's around 4 inches deep. It's actually 4.375 inches deep, which is on our diagram. Well, let's just turn that off. On our diagram, that would be this distance, and it would be 4.375. There. Let's see what else we have. This one is the flange thickness and the width of the flange, so we don't really need those for what we're doing. We don't need the stem thickness. Remember, the flange is this top part. The stem is the vertical piece, that the way I've got it drawn here anyway. Let's see. Then we get into this set of columns, axis XX and axis YY. So we have to go up here and see they've labeled XX as horizontal when you're in this orientation and YY as vertical. So with my beam, I was loading it, you know, the beam was turned sideways and I had loads all across here. There was a point load, a moment over here, a distributed load, but I was loading it this way. And if I look at the end, you know, those loads are in here like this. Those loads would be perpendicular to an axis that's horizontal. So they would be perpendicular to that axis, which is labeled as XX over here. If for some reason I had the beam and I was loading it on the side here, now the vertical axis is the one that I would be needing. I need the axis and the loads to be perpendicular to one another. So that would be the YY axis in here. Normally you're not going to use the YY because normally you don't load beams on the side. You can, but that's not typical. It's more common that the beams are loaded on the top somewhere. All right. So that sends me over to the numbers under the XX column. So I'm down here at the WT 4/29. There's the moment of inertia, 9.12. So I, from the chart, equals, and I'm just writing it down, 9.12 inches to the fourth. Notice the moment of inertia for the YY is 37.5. So they are different numbers, not at all the same numbers. So you do have to pay attention to get the correct one because they are very different numbers. All right. Let's see what else we have. We have S. We don't need that yet. We don't need R yet. We do need this number, which is labeled as Y sub C. So in their picture, they have measured from the top of the flange down to the XX, which is our neutral axis, Y sub C, which for us is 0.874. So that would be this distance. 0.8, I think it was 74 inches. Like that. All right, now we can go back over here and very first thing, maximum flexural stress. So it didn't say maximum tensile stress or compressive flexural stress. It didn't specify, it just said which one is larger. So an I-beam, what we did last time, this axis ends up in the very center because there's a flange at the bottom of the I-beam, and so that brings this to the center. And so it doesn't really matter if you measure from that neutral axis down to the bottom or down to the top, it's the same distance. But here, this neutral axis to the top is 0.874 inches, but to the bottom is a much bigger distance. In fact, it's 4.375 minus 0.874, 3.501 inches. So it makes a big difference if I put the distance from the neutral axis to the bottom of the beam in here versus the distance from the neutral axis to the top of the beam in here. So since I want the maximum one, and I don't care if it's tension or compression, then I'm going to use the negative, because I'm starting here and measuring downward, 3.5. So Y is negative 3.501 inches. And then I, we just looked up, forgot to write it down. Oh no, we did write it down right there. M is 10.8. So we can start plugging these numbers in. Sigma equals 10,800 foot-pounds. Now these are in feet, so I'm going to convert that 12 inches per foot. Y, now there's a negative sign from the equation, so there's the negative. Y is also a negative number, so times negative 3.501 inches. This negative is because I started here and measured in my negative Y direction. And then divide all of that by I, which is 9.12. And let's see what we get. If you forget to do your conversion to get to inches from feet, then you'll get the units all messed up. And it's negative and negative, so it is a positive term. Oops, that should be 0, 0. 10,800 times 12 times 3.501 divided by 9.12. Oh, we get a bigger number. All right. 49,751.1. And the units here, as long as I convert these, would be PSI. This number is positive, which is a tensile stress, which the bottom, if I were to color in here, I don't know, from here down, all of that is in tension. And remember, the further you get away from the neutral axis, you put bigger and bigger values for Y, which makes the stress larger and larger. So maximum tension is at the very bottom. The top of the beam, or anything above the neutral axis, that's all in compression. So all of this part is compression. And if you want the maximum compression, it's going to be on the very top of this thing. Now, if you change this and it's a negative bending moment, so this is negative 10.8, then these flip-flop. And the stuff I have shaded as red becomes tension, because now the beam is bending this way for the negative bending moment. So all of this is tension and all of this is compression. So you do have to keep all of that stuff straight in your mind of, where the neutral axis, that's what this is the transition point between the negative values for compression and the positive values for tension. It's not always true that compression's on top, tension's on bottom. That's true when your bending moment is causing the beam to bend that way. But it's possible for the beam to bend the other way. It's possible for the beam to bend both ways in the same beam. So it's not always true that compression's on top, tension's on bottom. This number, we had written down our yield strength of 53 KSI. So the factor of safety here is not nearly as large. Factor of safety for yielding is the yield strength, 53,000 PSI, over the yield stress, or the flexural stress, 49,751.1 PSI. So let's see what that is. I put two decimals in there. All right. 53,000 divided by 49,751.1. 1.06. So we do have, some factor of safety. We'll put it at 7. But that's not very large at all. So we're getting really close to, if anything is different from what we expected, if somebody drops a load on there and there's a little bit of inertia to go along with the load, then we have probably deformed this beam permanently because we're so close to the yield strength of the material. So this one would be a really kind of small beam for this particular load. Later on, not tomorrow, but later next week, we'll actually go in and figure out, if this is the load, what beam do we need to use to get a factor of safety that we want. So we would be able to define our factor of safety, go in and pick out the right beam for that load. But that's not today. All right, what do we need to do now is almost go back a step and generalize some of this. So we want to be able to go in and find the maximum flexural stress in the beam. So one way to do that is to develop equations that model all of basically this, but in terms of variables instead of hard-coded in numbers. So let's do that for a little bit, and that'll lead us into what we're going to do tomorrow, where we're going to take that same idea, but we're going to draw pictures to represent those equations. So let's just do a simple one. So a beam, this is a side view of a beam. it has a reaction over here and a reaction over here and a point load in the middle of it. Now technically these reactions are functions of that point load. You know, this reaction is P minus RB, for instance, and this one would be P minus RA, and you could figure out the actual RA in terms of P and the length and X and all this kind of stuff. You could do that. We're going to not do that. We're going to just leave RA as its own variable. Let's say that this length is L. This length, we're just going to call it A so that we can define where that point load is at. And then we'll measure in that direction as X. So this beam is two distinct sections. One section from X equals anything from 0 to A, and another section where X is between A and L, the length of the beam. So this section and that section. Now I didn't include the where X equals A. That's sort of a special point that it depends on if you're approaching it from this direction or if you're approaching it from the other direction. So we're not going to be too interested in that exact point right now. So here's what I want to do. I want to take and cut this beam open at some distance X, where X is between 0 and A, and draw a free body diagram of that. I'll draw it a little bigger so we have more room. So there's my variable distance X. We are drawing this side, so the point loads, actually we're drawing that. The point load's not on there, it's only RA. And we cut it on here where we need to follow this convention. And we can write our equations for summation of forces in y direction. And it just says, based on this, RA minus V equals 0. Therefore, V equals RA. So if I want to know, and I can even write it as a function of X, but there's no actual X variable over here. So the shear force anywhere that I would cut this beam from here all the way over till I get up to A, the shear force in there is a constant RA, so it just equals this value for whatever that reaction at A is. I could do the same thing for the bending moment. I've got, if I do the moments about this cut point here, I've got RA times X. I said clockwise is positive, this is counterclockwise, so minus M. And the shear force is on that surface, so it doesn't create a moment there. Therefore, M as a function of X just equals RA times X. So now I've got two equations that will perfectly model the shear and the bending moment anywhere from, on this beam, from X equals 0 to A. Now when I get to A, it does, get kind of odd on what to do with the point P. So we're not going to worry with that just yet. What if I do this section? So now this is X is between A and L, so it's over here. Let's draw that free body diagram. I should have left some more room for it. I don't think I did. Let's draw it on a new page. So we're going to draw this free body diagram. Now the distance X goes all the way from here. We have the point load on there, or well, the reaction at A, which is a point load. We also do have this point load, so we only cut off this little piece here, which does leave that point load P. It is a distance of A. And we have our internal shear and bending moment. All right, oh, stuck under there. We're all crooked. All right, let's do the same thing where we write summation of forces in Y and summation of moments. So here I've got RA minus P minus V equals 0. So I've got an equation, V of X is equal to RA minus P. So it's really not a function of X. Anywhere in this section from the point load over to the end of the beam, the shear force is a constant RA minus P. So it's just a constant value. Let's do the moment. RA times X minus P times this distance, which is X minus A. V does not go into that equation, minus M. We'll move M over to the other side, and M equals RA times X minus P times X minus A. So I'm getting a little bit more complicated equations, but this equation would model the bending moment if I were to take my original beam and want to know the bending moment anywhere from the point load over to the end. So I would know the entire bending moment. So at this point, now it's a very simple beam. It just had one point load. It was simply supported. But you could at least start to see where, if you wanted to, you could develop these equations and then take some derivatives, find the inflection points, and figure out where the maximum moment is. We're kind of going to do that next time, but we're going to do it in a graphical way without actually having to do the derivatives. Let's do one more of these with a distributed load on it, just so you see, reinforce the point, I guess. So there's our beam. We're going to put a distributed load, evenly distributed, all the way across this one. We'll still have RA. We'll still have RB. And we'll make this whole beam L length long. So this one is just one section, so it doesn't matter, if I cut it here, anywhere along the line, the section, the free body diagram of that section will look the same, unless I were to add some other features to it, like other forces. So let's just pick some random distance there, draw this free body diagram. This distance is X. Let's say our distributed load is just W. So W would be some pounds per foot or newtons per meter. We have RA over here, internal shear force, internal bending moment, and we can go about doing our same thing that we did before, where we did summation of forces in the y direction equals 0. We have RA. I guess I didn't put arrows on this, but I intend for this distributed load to point downwards. Now, this is a distributed load, so normally what I do with distributed loads when I'm writing these equilibrium equations is lump them. This would be W times X, and this distance would be X over 2. So this is minus W times X minus V. The moment doesn't go into the equation for Y. It doesn't have a line of action that's in any direction. So we're going to move V over. This time we really can call it V of X because we have an X in there. V of X equals, well, I did that twice, equals RA minus W times X. So now you can see where last time, let's see if I can find it, with just the point load over here, we had a constant shear force, at least in this section. Here, I've got a distributed load that's constantly applying more and more force, and I have a linear slope, you know, W times X. So there's a slope associated with this X, a negative slope, in fact, that is constantly changing the shear force as I move across the beam. Let's write the summation of moments about our cut area here, our surface. RA times X again, so that's the same as it was last time, minus WX is the force, and this moment arm from the cut over is X over 2, so minus WX times the moment arm of X over 2. Shear force doesn't create a moment, minus M. Let's move M over here. M of X equals RA times X minus WX squared over 2. So now I've got a polynomial, so I've got a curve in my moment. Last time I had a linear shape to my moment diagram. Now it's getting curved. So this distributed load is creating a different type of moment than the point load was. And so we're going to look at that type of thing tomorrow. Maybe, I don't know if you would think of it as more abstract or not, but what we're going to do is we're going to generalize this even further and look at a set of if-then statements. So if we have this kind of load, then the shear force will look like this, or the moment will look like this. And that's what we'll do tomorrow. What I'm going to do next is kind of just a little bonus for a machine, because it's a tricky one that some of you are doing for homework. So I'm going to give you a hint on how to do it. So here is a little setup for this particular problem. Has to do with bolt cutters or wire crimpers or something like that, where it's a machine, it's not a frame, because the parts are intended to move relative to one another. And this little bolt cutter or wire crimper or pair of pliers or whatever you want to think of it as, has a handle, kind of like this. I'm simplifying it, but it's got a handle like this. It's got a hinge and a hinge, or a pin and a pin, I guess maybe would be better. You're applying some kind of force over here to squeeze these things together. There's the jaw. And this this pin, let's call it D, is pinned right here to D. This pin C is actually pinned to the other handle, so it'd be a mirror image of the handle down here if you wanted to deal with that. And here I've got, we'll call this A. This is pinned to this little piece. And then there are mirror images of these down here. I guess I can draw and it doesn't hurt. So there's the other C. And over here you would have, I guess, what letter were we at? E. There would be E. There would be the other B. So this is it taken apart. A lot of times with machines, you have to start by taking them apart. In fact, in this particular one, you're actually given this force F, 10 or 20 pounds or whatever. And you're trying to figure out how much clamping force you have over here. We'll call it FC. And so you have to work your way through figuring out what's going on at all of these pieces. So Normally, when you're working with one of these, it's best to start with the place you know something. So you know this one. Let's say it's 20 pounds. So that kind of gives you a clue that maybe you should start with this piece. So pin C is holding this other piece together. These are not two force members. You've got two pins, but you've got a force over here applied to the handle, not to the pin. So I'm going to have to treat this as CX and CY, which would put over here the opposite, you know, CY going down and CX going to the left. D is pinned over here to the jaw. It has two pins, but it also has a force, the one that, you know, you're actually clamping onto something over here. You know, I don't know what it is, but you're clamping onto it, so there's a force inside here. So D is not connected to two force members, so you just have to do DX and DY, which on this one, since you assigned them over here as right and up, over here you have to assign them as down and to the left. Then you get to A. A is pinned to this little piece right here. This piece is a two force member. And so when you figure out this is a two force member, then you remember you just have to do force in AB. You don't have to do AX and AY. Here, you just have to do the opposite force, same magnitude, opposite direction, so that when you put it back together, these two cancel each other out. Here, you could do the same thing. Here at E, you could do whatever you wanted. EY, EX, and you could put the matching ones over here, so EX and EY. And then you got the, you don't even really need these, I just drew them so that you had the whole picture. But what happens once you get all of here, because you started here, right? And you ended up with 4 unknowns. So you couldn't solve for all of these because you have too many unknowns. So you draw another piece. Here, as long as you see this is a two force member and not a place where you have to put AX and AY, now it looks like 1, 2, 3, 4 unknowns, except there's a little subtle trick where if you write for this piece, summation of forces in the x direction equals 0, then dx is the only force that goes in this equation. Therefore, dx has to be 0. So if dx is 0 here, then dx is also 0 over here. On this piece, if dx is 0, then you write summation of forces in the x direction equals 0. You end up with, well, dx is 0, so I have 0, plus cx. So cx has to be 0 also. And now you get down to a piece where there's only 2 unknowns and a force over here to work with. And so you can actually solve for dy and cy, bring dy over here. Then you can solve for AB and FC if you want to. So it's kind of a little subtle thing, but it's only one of those where if you see the two force member, if you don't see the two force member, then this one ends up with too many unknowns to be able to solve with pure statics methods. And you'd have to go into some kind of energy deflection type methods that we aren't talking about in this course. So I just want to put that in there in case somebody was having trouble with a problem like that one. It would give you a little extra hint on how you might go about doing that. All right, we'll be back tomorrow. And tomorrow we're going to go into drawing shear and bending diagrams. So actually drawing pictures of what these equations are telling us. So we'll do that tomorrow though. All right, see you tomorrow.